Hello and a very welcome to our 2 days little online seminar out of our series of online seminars we're doing this autumn here. It's about cable testing and network testing. My name is Alfred Huber. I'm here at Softing IT Networks, the technical manager. I'll take you through the presentation today. As usually, I'm not alone here in the studio, so I got a co-pilot here as well. And the gentleman wants to introduce himself and his role. So
I can try it. Yes, a warm welcome from my side as well. My name is Matthias Carven. I'm the head of sales and marketing for EMEA here at Softing IT Networks here in Haar. I'm at the moment the co-pilot of Alfred. So Alfred is the host of this webinar. A short brief information is you have a dashboard on your right or left side on your PC. The dashboard shows you a column called handout, so you can download the PDF from this presentation. And there is also a column which is called questions. You can type in some questions, send it to me. I will collect them and we will answer it at the end of the webinar. If you have any questions during the webinar, please give us a short note. Maybe I can answer it direct or we will answer it later on. So that's from my side. I will go to my desk and hand over to Alfred. Good luck and hopefully good information.
Matthias, thank you very much for assisting here on this webinar today. So what's the topic of today? It's fiber optics again. So this is following up the basic course of last week. Now we are doing an advanced look into the fiber optic stuff today. So let's start with the agenda of today. For the ones who are new to our webinars, a quick introduction: who is Softing? Then we're going to talk again about fundamentals of the signal transmission on optical fibers, and a very important topic. We put it last week on the agenda as the last topic today. It's very prominent here as the second one. Before we start already going into the details of test and measurement, it's inspect before you connect. So inspection of end faces and cleaning of end faces of fiber optic connectors. Then we're going into the different types of test and measurement equipment, as we already spotted last week. And then we are going into very detailed into attenuation measurement and into reflection measurement, the two main ways of testing and measuring fiber optic systems. So let's start with the introduction of Softing. Very briefly only, Softing, a typical German mid-sized company. Headquarters is in the near of Munich here. Let's say it's Munich. Company was founded in 1979, and went public in the year 2000. We are about 80-90 million of turnover, and we are about 400 employees spread around worldwide. Let's say most of the people here at these headquarters in Munich here. Softing itself, the business sits on 3 columns, as you can see over there. The 3 columns are automotive, IT networks, and industrial automation, as its complete name is. So what is automotive doing? Automotive is designing and developing test systems for EPUs, for control systems of the car, and helping car manufacturers in designing these kind of things. Industrial automation, what is industrial automation doing? They are providing instruments called gateways. Gateways are translating modules, let's say, on a production line to connect different machines together, speaking each individual different language of a machine. And to make it a complete production line, you need interpretation, translation of these protocols, and these are gateways called. And they also have a new feet on the ground, which is data collection on machines, for machines to do some proactive maintenance on these kind of machines. What are we doing? Softing IT Networks. We're sitting in the middle, and we are doing test and measurement equipment actually for building installation, universal cabling in building. So what is the relation to the other guys here? The relation is quite simple, because in the automation world, in the industrial automation, our famous protocol out of the businesses, of the offices, Ethernet is moving into this. And moving into this means when Ethernet is moving into an application area, it's bringing its topology of cabling with it, and the topology of cabling needs to be tested. It needs to be tested more or less the same way as it's tested in an office building. And similar things are happening now to automotive. As we know, the automotive is also moving into Ethernet, and especially Ethernet is moving into cars when it comes to autonomous driving, where you need very quick and high speed communication within your cars between the sensors, the cameras, and all these things which allow us to leave the steering wheel alone and let the car drive. Okay, so IT Networks, we are the ones to provide the test and measurement solutions for all these applications. Where are we located in this world? So here's a quick look to the map of Software IT Networks. So the headquarters is in Munich, as you can see in the middle. We also have a excuse me. We also have a strong branch in America, in Knoxville, Tennessee. Very nice place to live. We also have a very strong branch in Asia Pacific. It's Singapore, where the R&D for the high-end instruments sits, and also the sales taking care of this Asia Pacific market. Then we have sales office, dedicated sales office in France, in Lyon, and we have in Barcelona a sales office. Then we have in Vienna a sales office, and also in Milano in Italy, and also a very strong sales office in China, in Shanghai. So this is our little world we're working in. Let's have a quick look to the instruments we are providing to the market. So we have grouped the instruments in mainly three groups, starting top down. The top of the list instruments, the most complex and most expensive ones, are the certifiers, which we're going to talk about today, certifying fiber optics. Then we got qualifiers. Qualifiers also determine the transmission quality of a transmission line, by doing this with an application control mechanism, doing it with Ethernet control. And we have the beginners level, let's say, the verifiers, just to check, for example, for proper wire map, or on the fiber optic part to give some visible light indication of cable breaks and so on. Okay, quick look to the instruments. Let's start with the first topic on the agenda. It's fundamentals of signal transmission and optical fibers. First question, where do we find these optical fibers? So optical fibers, here, a typical example of a company spread around a certain area. The company consists out of 3 buildings, A, B, C, and takes a certain area, a certain local area. So what we're talking about is called LANs, L-A-N, local area networks. And how to bring communication into these 3 buildings, or to connect these 3 buildings, the first we start is a fiber optic connection between the 3 buildings. So that's typically done in fiber optic in single mode quality. We will get to the details a bit later, the difference between single mode and multi-mode. Okay, then if we move into the building, we have to connect the different floors together, and we do this as well with fiber optic cable. Here we are changing most of the time to multi-mode, so difference will be seen later on. Okay, and when it comes to the actual floor, interestingly, we are completely changing the media. We are going then to copper networks typically. We did it yesterday and the week before. We very extensively talked about that area. Today we are staying here on this level here, on the primary and secondary level. There's also a fourth group of applications which we nowadays find in a building. It's Wi-Fi. Wi-Fi is not a topic of this little seminar series, but it's worth to mention because there's no network nowadays without any Wi-Fi connection. So now let's talk about the difference between multi-mode and single mode. What you see here is a piece of fiber optic cable, multi-mode cable, and a single mode cable. So what's the obvious differences? The obvious difference is the diameter of this inner glass here, which is called the core. And this core is in a multi-mode cable, it's about 50 micrometers. In an older one, it was 62.5 micrometers in the lower range. Okay, and that's multi-mode cable. So we have these 50 micrometers glass core, and this glass core is surrounded by a different type of glass, but it's still glass. And this glass is called the cladding, and the cladding has a diameter of 125 micrometers. Okay, so that's multi-mode cable. What's a single mode cable? Single mode cable, starting from the outside, also has a cladding which is 125 micrometers. So the glass part in it is the same diameter. But the difference comes now to the core. The core here is very thin. We're talking here about only 9 micrometers, very, very thin. Okay, what's the background of this? Multi-mode, what does multi-mode mean? If we send a pulse of light into this fiber optic cable, we do it either through an LED or some VCSEL lasers, and this pulse is just turn on the light and turn it off again. So this light turned on will immediately bring a number of fiber optic lines, let's say little waveforms out of this transmitter, and we get a series of so-called modes which are part of this pulse we are sending out. So in a multi-mode cable, we find now that this pulse is consisting out of different modes, and the modes have different ways to travel through the data cable here. So we find modes which are going straight through, and we find modes which came in with a certain angle and got here on these connection of the core and the cladding of these surface. They got reflected, and they got reflected again and again. So we got a series of modes in this cable, and unfortunately, through to these ways they are going through the cable, we got this effect, what you can see here. It's a modal dispersion. So you see that the pulse, which was very sharp when you just send it in, now is spread out. And since the energy has to stay the same as sent here out, it also gets down in amplitude. And this is the limitation for a multi-mode cable. If a multi-mode cable would get too long, these differences in the modes traveling here through would cause this pulse getting extremely low on level and also very wide. So that's a limitation of the length of the cable. Another limitation in a multimode is if you send now a second or a third pulse very quickly after the first one, and after a certain length of cable, it would look like this one. It would happen that the pulses can't be separated anymore because the slowest mode from the first pulse might be even slower than the fastest mode from the second pulse. And you cannot clearly distinguish between the individual pulses. So you get a limitation in length for the cable, and you got a limitation in the speed you can transmit the signals in this. Okay, how to overcome this? How to overcome the length criteria? The length criteria you can overcome when you make these core very, very small. We just limit it down to 9 micrometers. 9 micrometers means that we also filter, let's say, the modes, and only one mode is traveling now through the single mode cable. Okay, that allows us to send in a pulse. And after a certain distance, the pulse is still almost the same width as it was when we started the pulse. It's getting down a little bit because we got some attenuation on this, some losses on the cable. We see later the reasons for. But when we're here talking about this distances, we're talking here about up to 40 kilometers. Some modern fibers go up to 100 kilometers. Where we talk on distances here on multimode through these effects, we are down to a maximum of around 500 meters. So that's the choice for the long distance, and that's the choice for the short distance or medium distances. Okay. Just a quick overview about the difference between multi-mode and single mode. So if everything is okay, these signals are traveling very nicely through the cable, and hopefully the cable is not too long and the pulse can be read by the receiver on the other side. What are now effects which are causing trouble in the run of these modes? There are two basic effects, groups of effects. One are called the Rayleigh effects and the other one called the Fresnel effects. What are Rayleigh effects? This is coming from little particles in the fiber optic cable itself. You see, here is my beam of light, which is traveling through the core, but there are little particles in the fiber optic cable itself. And this leads to reflections, deflections, and the light spreads out a little bit. So we lose our light energy through to this construction, let's say, of the core. We can't get them out of this core. Okay, and you see after a certain distance that the signal getting lower. Okay, and if you're talking about reflection, there are also reflections happening directly back to the transmitter, but they are down to the level of about 1 ppm. So 1 part of a million of the injected signal is only directly straight reflected back. But we need sometimes this reflection, especially when we work with so-called OTDRs, test instruments which are based on the reflection of the cable. And these instruments are, yep, they cost a certain amount of money because the optic has to be so good to detect this very, very small level of reflected energy. Okay, let's come to Fresnel effects. What are Fresnel effects? These are coming basically from connectors used in fiber optic. As we learned last week, fiber optic connectors are typically male-to-male put together through a coupler. So there is no female and male as we have on RJ45 on copper. But usually on fiber optics, we have always 2 connectors which are put together through a coupler. And of course, it's a mechanical connection, let's say. So there's always a little amount of misalignment in the sleeve where we end up with the connectors. And if you see on single mode, we have a core diameter of 9 micrometers, and we only have a sleeve with a little tolerance, which a tolerance of about 1 micrometer. We already lose 10% of our, let's say, area we meet at the connector points. So mechanical precision is very important in fiber optic connectors. This misalignments cause, of course, loss of energy, and what is more important is also reflection of energy. So we got here a higher amount of reflection of energy on a connector. Typically, if you see a connector on an OTDR, you always see that the connector itself has some reflection and has some loss in the signal on its way through the connector. Okay, what else do we have? Where are these problems coming from, these reflections coming from? Most of the time, honestly, they are coming from damaged or dirty end faces of the fiber optic connectors. So that's a very important point, and we will have a close look to the cleaning of these fiber optic connections. Okay, breaks, insufficient terminations in the connector, bad quality of workmanship can all cause this trouble that we get too many reflections and lose too much energy in this. Okay, now let's talk about these end faces and the cleaning and the inspection of these end faces, because that's absolutely very important fact we have here, we have to take care. So dirt is our biggest enemy in the fiber optic area. This is why it's so important to have always the capability to inspect the end face and to clean the end face of a fiber optic connector. And when do you have to do this? You have to do this each time before you do a measurement, of course, and each time before you do a connection. That's very important. So, and you have to clean both sides of the story, both connectors. Also very important to make sure that there's no little stone in between the connectors and gives you enormous trouble. Here you see a few pictures of events which are causing trouble in the connector connection. Okay, very important, if you want to clean something, use the proper cleaning tools. Don't fiddle around with your own stuff you have, so make sure you have proper professional cleaning tools. Cleaning liquids you can use. You see later a little bit a picture of this kind of stuff was available. Nowadays we moved away from the alcohol, from the IPA alcohol. Now it's more water-based cleaning fluids, which don't leave any residuals on the connectors. And what's very important, or very popular nowadays, you can see here, are cleaning pencils. So this is the first choice of everybody nowadays to clean the connector end faces. Also important, of course, is before you start cleaning, is to inspect the end faces. So make sure that you get a proper microscope. You can watch these, you can see this end face of the connector, this core of the connector. And don't believe this. There are people out there, they tell you they can see whether there is some dirt on a fiber optic connector. We're talking here about micrometer stuff. Nobody can see this without a microscope. Okay, there are also simple handheld devices. People might have seen this already. That's not the thing we want to have. We want to go to more professional automated electronic microscope, which are also connected to certain software, because the software in the background makes a decision. Is this connector really clean enough, or is it not broken? Is it clean enough to do a proper connection, and can it guarantee the proper amount of light will travel through the connector? Okay, a little word to the protective caps you see on the panel over there. Never remove them without any good reason. So just removing for testing and remove it for patching. People sometimes need to see pictures what's happening when you don't do it properly. And I found a very interesting experiment on the internet, and I copied the result of this to here. So somebody took a sample of about 20 links, and he had 20 connectors in the middle of the links. And he did measurements on the attenuation, so here, and he did measurements on the reflection of these connectors in the middle. Okay, so and he did it in two ways. First of all, the connectors, the 20 connectors in the middle, were really pretty clean. And then the second one, he just opened the connection of these connectors and put it, moved the fingertip on top of this connector. And it's called here finger oil, what you see now on the connector. And if you reconnect this connection and you repeat the measurement, first of all, you will see that the attenuation gets higher. So we are missing more light, which is traveling through here, this connection. But the worst experience he made is that the number of the measurement results of the reflection just dropped down, and they dropped dramatically down. And you see this red line here, which is at 45 dB. This is the reflection value for a single mode connector. And the single mode connector should not be beyond under this red line. And you see the first measurements which were done by with the clear connector, everything is fine. We are always on top of these 45 dBs. And now when only this little finger oil comes into the game, you see the difference here. And here we're about 20 dB different in the reflection value. And so we get too many lights directly reflected back to us. This light is missing on the other side. So if that's a long link, it might not be sufficient to get a proper value to the receiver and to be worked on this. So everybody can repeat this experiment and very easily with an OTDR. And what we have done here is this is a single mode connection, 2 connectors. And the first one was done with this here, with clean connector, the first shot. And you see that we have a very nice little reflection and very small attenuation. If you open this up, and what we have done, we just put it down to the carpet a little bit, both connectors, then reconnected this, and then we did a reflection measurement again in the OTDR, and you see that the reflection dramatically lifts up. And what you also see is that the attenuation is also above the limit already. So it's just a little few particles on the connectors are getting this result. And there's some statistics on the internet where you can see that about 85% of all network failures where fiber optic is involved are down to dirty connectors. And this is why it's so important. And it's absolutely necessary that everyone who is dealing with fiber optics on the construction side has to have some microscope capability and has to have the proper cleaning material, because this dirt is so important and can cause so many trouble. And to bring us to a higher level, there are even standards behind this job of inspection and cleaning. Okay, let's see. So everybody's looking at this picture and you see they look very clean here, these 2 connectors. But are they really clean? Are they clean enough that they can transmit data without getting any losses? Okay, how to determine the word clean? When is a connector really clean? To bring here some level to this is there's a standard. There's a standard called 61300-3-35. This standard is defining when a fiber optic connector end phase is clean. How does this work? Here is the microscope. The microscope is taking the picture. Picture is loaded into the tester, let's say, here in OTDR. And then this software is putting cycles around the core, 4 cycles, depending on single mode or multi-mode, the distance from the middle, let's say, and is allowing every area here, it's allowing a certain amount of dirt or a certain amount of breakage, allows some problems on the connector, but make sure that that this level is not influencing the data transmission over this connector. Okay, so we get a neutral situation, a standardized situation where we can say a connector is clean or is not clean, or is broken or is not broken. Okay, so very important that you have these kind of microscopes combined with an instrument to doing these analysis. Just when the connector is clean, we can use it for connecting it. Okay, and if it's not clean, what are the common cleaning methods? So I did a survey on the construction sites and I found very interesting answers. So let's start with the first one. Okay, just wiping the connectors on the sleeve of the shirt. Very popular. Okay, what else did I get as an answer is wiping the connectors with your finger. Clean the dirt, mechanically clean it off. What else did I get? Blow vigorously over the end face of the connector. What does this mean? Okay. Cleaning with water. I found an installer who had a glass of water next to him, and he put in the connector and he was shaking the connector to get the dirt of this connector off. Also a cleaning with plenty of mild alcohol, very nice liquor next to the construction, and always use this as a cleaning material. Or very common, cleaning with paper handkerchiefs. Okay, of course, all these methods I learned are complete nonsense. Don't do it. Don't do it. You get more dirt on the connector. You are destroying the connector. Cleaning with water, the connector is soaking in the water. Don't do this. Okay. And to get some systematic into the cleaning, there are also standards out on the market. which are defining proper cleaning methods. Okay, I don't want to go into the details of these standards, but there are standards. It's defined how to clean properly. Okay, and if you want to use tools for doing proper cleaning, there is also a bunch of tools which are the proper ones. You see here, it's called one-click cleaners. I mentioned earlier, you see here fluids, water-based fluid to clean it, certain different tools you need, also compressed air and things like that. So there's professional tools out on the market to clean. Don't do the other ways I just explained to you. Okay, so after we settle this with the cleaning, let's go now to testing and measurement. What different test and measurement types are available on fiber optics? So the first one, the basic one, is a very simple fiber optic continuity test with some visual fault locator. Then we got power measurements. So we are relying on a signal coming from the outside into our network, and we are just checking the power level of this. Okay. Then we're doing a qualification test. This is the first way to really find out what the bandwidth of the fiber optic cable is, qualification. And then we come to the real acceptance testing or acceptance measurement is loss measurement. So we are determining the amount of data of energy we lose over the fiber optic line. And there are two different setups of these loss measurement instruments. First of all, the standalone optical loss test system, OLTS, like our Fiber Expert 700 you can see over there. And then we have very common these integrated modules for the LAN certifiers. So the typical copper certifier is turned into a fiber optic loss measurement system by just exchanging the modules here in the back. Okay, and master's class over there is reflection measurements used in OTDR, done with an OTDR. Okay, these are the current actual types, different types of doing test and measurement. Let's start with the fiber continuity test. That's very simple. We are using a visible light source here to do this kind of testing. What we're trying to find, first of all, we try to find out polarities. That's not mentioned here. Do we have the proper polarities? Do we have the proper crossings between the beginning and the end of the fiber optic cable? Things like that are done with visible light. And also things like here, what we see here is determine defective connectors. You see here the whole connector, the whole ferrule of the connector is glowing. That's not the right way. It should only have some little light spots here in the middle coming out, and you see here, that's the way it should be. So here, this patch cord is definitely broken in the connector somewhere because it's glowing all around. So these type of faults you find with a fiber continuity tester. Here is a picture of one, so the marketing part of this. So it's the VFL 5000, which we offer on our portfolio. Let's come to the next level, to power measurement. These power measurements are usually used in an FTX environment, let's say, and they are relying on a signal that's coming from the outside. For example, the provider is giving us a certain amount of energy we have to get on these crossover points. So, okay, that's a measurement where we rely on the outside incoming light. Okay, if you want to find out the performance now of your fiber optic cable, qualification is the first one. So we are testing here against the application. What we are doing is we are taking our fiber optic cable in between two test instruments, two NetExpert XG2s, and we are doing a BERT in between, so a bit error rate testing, and we are looking for the number or the amount of data getting lost between the two ends of the cable. So same as in copper, we have a certain allowed tolerable number of failures we allowed over a certain time. If we test, for example, for 10 seconds on 1 gigabit Ethernet, it's not allowed to lose one data package, one individual bit. And if we manage not to lose data between these fiber optic cable from beginning to the end, so we can give the statement, this cable is capable to do 1 gigabit Ethernet, or this cable is capable to do 10 gigabit Ethernet. Also very important, in this instrument, it's included the analysis of the end phases. So the NetExpert, as you can see here, is working together with our microscope and is providing this analysis of the end phases. Okay, this end phase doesn't need any analyzing. You see it immediately what's going on here. Okay, so very important part of the instrument. So let's come now to the field measurement methods, to the acceptance test methods we have. So the first one, there is two different levels. The levels are called Tier 1 and Tier 2. And the first level is the light source power meter method. So we have On the one side of the link, we have a transmitter who gives us a certain amount of light. On the other side, we have a power meter which receives the light, and we are finding out in between what is the loss of the cable. Is this loss of the transmission line within the specification for the cable? And that's the way how to determine is it properly, can it be used or not. That's tier one. It's attenuation measurement plus length determination, length measurement in between as well. Okay, excuse me. Tier two is a combination of loss measurement and power meter plus OTDR. So OTDR is here the hero of the measurement. And OTDR is an optical time domain reflectometer. It's sending out pulses in one end of the cable, and it's receiving reflections out of the cable from the same port, and it's analyzing the reflections coming out. We see later on a graph how this works. And we get here a very good localization of events on the trace, on the distance of the cable here as well. So that's helpful to find out where is the problem on the fiber optic link, for example. But let's first start with the attenuation measurement. And before we dig into the attenuation measurement, maybe some general rule about standardization standards. So when a new Ethernet comes to life, let's say, when a new transmission system comes to life, it always starts with the active protocol. And after this, this one defines a minimum requirement on the cabling that might transmit this new protocol cabling. Okay, and when this is settled, the cabling standards are settled, the limits are given, we start with testing this. Okay, that's the hierarchy of how standards work. Works from top down. So starting with the first level is the application standards. Here you see a bunch of IEEE Ethernet standards based on fiber optics, 40 gigabit, 100 gigabit, and so on. All these active standards have in their standards already defined a minimum requirement for the cabling which can be used to transmit that signals. So the people who are writing the cabling standards are now working on these minimum requirements and make out of this, they make the cabling standards. This means they take the minimum requirement and put some necessary headroom to the limits to allow certain deviation of the behaving of the system. Plus, they also allow certain deviation of the instruments testing this cabling standards then. So the last one in the row is the measurement standards we have, and these standards are defining how good an instrument has to be. They are defining the measurement methods, how to test these cablings defined here in these standards properly. Okay, and you see for fiber optic, we have a bunch of standards for installed cabling. Unfortunately, this bunch of standards is sometimes having some contradictions in it to other standards. So you have to be very careful what standards to be used and what one standard is allowing, and you have to clearly state against what standard you are doing your measurements. So currently the most popular standards for measuring and testing fiber optic links is the last one, the last row here, the ISO IEC 14763-3, which is the most popular one, and most of the test instruments are working around this. Okay, coming back to the applications here, there are various ways nowadays to transmit data over fiber optic cables. So depending on the speed of the transmission you want to have, it's involving a certain number of cables. It's involving certain technology which is possible to be used. So if you just want to transmit 10 gigabit Ethernet, you need just one transmission cable and one receive cable. That's what you need. A pair of cables you need. The typical bandwidth of a fiber optic cable is 10 gigabit Ethernet. There are also cabling now in the market with 25 gigabits. So if you want to get faster, you have to use a better quality of these cables. If you want to go now up to 40 gigabits, there's a simple trick. You just need 4 of this one. 4 times 10 gigabits, and for both directions, and we get 40 gigabit Ethernet transmitted. If you go up to 100 gigabits, guess what? You're just taking 10 of them or 4 of the 25 gigabits. What you see here as well, you see here something different. You see different colors. So that's also a way to utilize the cable with higher bandwidth, with higher load, you're just changing the number of carriers. Usually we have one wavelength, 850 nanometers or 1300 nanometers, and this is the working wavelengths, the carrier frequency, let's say. But in this case here, we are using a short wavelength dense multiplexing system. So we're having here 4 carriers, 4 different wavelengths. So the signal is split up in 4 wavelengths and transmitted, let's say, these colors in parallel over one cable. And this multiplex signal is demultiplexed on the other side. And you get on one pair of cable, you can transmit 40 gigabits. The same works for 100 gigabit, and the same works even up to 400 gigabits of data. So you're combining a higher number of cables and combining a higher number of carriers you're using to transmit the signal. Okay, this is different. These are the ways how you transmit Ethernet signals, higher frequency signals. Okay, what's hindering our signal transmission? It's attenuation. And coming to attenuation, you see here is the way, where is attenuation coming from? So you have the transmitter here, a light source here, and you have the power meter on the other side. So what we have in between? We have in between, let's start here with the main effects, it's connectors. Connectors which are mechanically fit together through the coupler. And the standards say if you have a connector, it's allowed to have an attenuation, a loss of light of 0.75 dB for a standard connector. Okay, when you look to the typical connectors nowadays, they are much better, so 0.3 of a dB, something like that. So what is the next factor in the attenuation? It's the cable itself, the fiber optic cable. So the standard is allowing here, for example, on a multimode cable between 3 and 3.5 dB per kilometer on 850 nanometers. It's getting down less on 1300 nanometers, as we saw last week, where we have these characteristics, attenuation characteristics of the cable. On single mode, we are going down to 0.35 of a dB of a cable. Typically, the standards is varying, depending on the sort of cable, is varying between 1 dB and 0.4 dB of a cable per kilometer. Okay, then we got also splices here in. Splices means direct connection of fibers without connectors in between. So we are allowed to have a loss here on a splice about 0.3 of a dB. What's in the practical world, you can get much lower. If you use some fusion splicing, you can go down to 0.0532, something like this. Very, very small attenuation, almost invisible attenuation for an OTDR. But there are also a mechanical splices in offer of various manufacturers. And the mechanical splice is always a bit higher. We're talking here about 0.1 to really up to 0.3 of a dB for a mechanical splice situation. And all these factors are now added up to give me some limit value. That's the way it works. Okay, measurements done with standalone instruments or with fiber optic modules and copper. We don't discuss here these dB calculations here. So loss is always reported in dBs, relative measurement. So where we get these values actually from here, what are the standards? So you can see a picture of the standards or some excerpts of the standards from the ISO standard here, for example. And you see certain different sorts of cable, categories of cables got certain different attenuation values, and that's the basis for your calculation of the limits. Just look into the standards and see what the limits are. The same for single mode, as you see on the lower part of the picture over there. Also for connectors, here is depending on where you connect or what connectors are you going to connect. If you connect just some standard connectors, standard against standard, we are down to 0.75, which is the allowed loss of signal we have in the standard connection. If we have reference connectors, they have to be much better. We're talking about 0.1 of a dB. Where do we need reference connectors? In test cords. So we have to make sure that the test cords are really of highest quality. And if we connect now a reference connector together with a standard connector, we are down to 0.3 of a dB or 0.5 in the ANSI tire. It's a little bit of moving target at the moment. These fiber standards are just being reworked worldwide. If you have a splice, the splice is fixed to 0.3 of a dB, whatever it is, a fusion splice or a mechanical splice. That's one way to determine limits of a fiber optic cable. The second one is more related to the application, which will be used later on. So if you base your limits on the application, you do it quite different approach. You're looking to a table like this one here where the applications are listed, and you know what quality of cable you have. So if you have, for example, a high quality multi-mode cable, OM41, you see the purple color here in, okay, and you try to transmit 10 gigabit Ethernet over the OM4 cable, then you go into the table and look into this, and you see that 10 gigabits allows you a maximum channel attenuation of 2.9 of a dB, and the cable is not allowed to be longer than 400 meters. So this is also a way to set yourself limits when doing the testing. So if you want to do 10 gigabit Ethernet, test the whole channel, the whole transmission channel, and keep to these limits here. That's also a way to determine is this cable capable to run 10 gigabits or not. Okay, now we are moving into doing measurements. Now we defined already how to get limit values. Now let's come into measurements. So there is a basic rule when doing fiber optic measurements, loss measurements. You never ever connect the cable under test directly to the measurement instruments. Even when it's a channel and it will fit very nicely to the instruments, don't do it. We always use test reference codes to do the connection to the fiber optic link. Okay, that's the golden rule. If we employ test reference codes, we have to make sure before we do the measurement to get the influence of these test reference code out of the measurement. And how do we this? We're doing a set reference, okay? And this set reference is defined in the standard. Interestingly, there are different ways to do this set reference to get the influence of the measurement codes out of the game. And there is in the standards 3 ways defined: reference with 1 jumper cable, so 1 test cord, reference with 2 reference cords, and reference with 3 jumper cables. So it's 3 different ways. And if you look into detail on this, this is the picture behind it. This is the way how it's done. Okay, and just a statement. So always try to use a single jumper reference method to do the referencing. Okay, because this gives you the highest accuracy in the measurements. Using a 2 jumper reference induces already errors into the measurement, is increasing the measurement uncertainties. Okay, and this method is even not supported by the latest and greatest measurement standards anymore, because it's injecting measurement uncertainties. What is allowed is this 3 jumper measurement or referencing here. 3 jumper means 3 test reference codes, high precision reference codes, are connected together and give you a zeroing of the system. And this is allowed to be used when this interface of the system itself is not possible to bring it to the receiving ports. Okay, for example, when you work in industrial environments, sometimes there are really big fiber optic lens connectors. This one can't be built into a receiving instrument, into a power meter. Therefore, you need to help yourself with a 3 reference code zeroing, okay, using these special cable in between with a special lens connector here. And after the referencing here with the 3 reference codes, you just remove the middle reference code and replace it against the device under test. Okay, so make sure using the proper referencing. Here again, the limit values that you saw earlier out of the standard, and now we use this to do calculation to bring it into our measurement system. Okay, here is an example of how to determine and how to calculate limit values for a measurement. What we got here is 100-meter fiber optic cable in between 2 panels. Okay, that's fine. And we want to do the measurements, so we are using a light source here on my side and the power meter on the other side. The instruments are connected through test reference codes, high quality reference codes on both sides. So now we want to determine what is the maximum value, the limit value of attenuation we have in between these 2 ends. Okay, we are starting now with the length of the cable here. So we got 100 meters of cable here. Maximum allowed attenuation for these 100 meters on multimode 850 nanometers is 0.1 of 3.5 dB. Okay, so 1/10 of the kilometer value. How many connectors do we have? We have 2 connections in the game here, and these connections are connections between a reference connector and a standard connector, which gives us a maximum attenuation here of 0.3 of a dB. So if we now sum it up, we're ending up with a limit value of 0.95 of a dB for this link on the measurement. Okay, it's a 100-meter link and it's 2 connectors built in here. Okay, if you go to 1300 nanometers where the attenuation is lower, we are down to 0.75 of a dB. If this would be a single mode system, we are doing the measurements here. The attenuation, the allowed one, is a bit higher because of the problem with the centering of these very small cores, and you are allowed to have here on this link 1.1 dB. Okay, but it's important. It's based also on the inclusion of the reference system. If you do a different referencing with 2 jumpers or 3 jumpers, these values are going to be changed because you already took connectors out of the measurement beforehand. So you have to change the calculation a little bit. Or you use an instrument that's doing this calculation more or less automatically. Why are we so keen now to use these high precision measurement codes nowadays? This has to do with the development, with the challenges we see over the years now in the fiber optic cables. So when I started in fiber optic, we were living on loss budgets between transmitter and receiver of about 13, 14, 12 dBs. To have 12 dB loss of signal on a fiber optic cable, you need an optical attenuator. It can't be as worse to provide these high values. And in the old days, the manufacturers for optical attenuators really sold enormous amounts. The idea is not to oversteer the receiver with too high energy from the transmitter. And this picture has completely changed. Now we are down to levels 1.9, 2.5, 2.9, 2.6. So the digit behind the comma around the dot is now getting very important. And to make accurate measurements on these small levels, we also have to tune a little bit the measurements. And the measurement uncertainties, we're looking into the effects of measurement uncertainties, where they're coming from. So one of the basic reasons for pure uncertainties is pure quality of the reference codes. If you lose more accuracy in the reference code as you have on the whole system, it doesn't make sense. It's not a measurement anymore. And to achieve these high values of needed measurement uncertainty, you need defined reference codes. In these days, we just use patch codes to do the measurements. The accuracy was not very important. We allowed 1, 2 dBs of measurement uncertainty, and this was always covered by the patch codes we were using. Nowadays, if you do proper measurements, use proper high-level patch codes to test, reference codes to test, no patch codes anymore. The next story was, what test signal do we use? So in the older days, we used everything which just emits lights. We used LEDs, we used pixel lasers, we used all kinds of these transmission things. Nowadays, it's different. We have to define a certain quality of light. And the buzzword behind this, you see on the other side, on the remedies, you see it's encircled flux compliance. What does encircled flux mean? Encircled flux, we see later on a slide, is defining the quality of the light. So we are defining a certain light beam, which is the test beam to do all these measurements here. Old story, uncalibrated measuring instruments. So every instrument which is a measuring device, not a testing device, but a measuring device, needs on a regular basis calibration, controlling of the accuracy against higher quality standards. Okay, so typically in our area, once a year the instruments have to be sent in for recalibration. Okay, so what we're going to do to keep up the measurement accuracy is using proper test reference codes, using proper light source, and making sure the instruments are fully calibrated and working properly. A last word on these encircled flux here. You see some very nice pictures how this energy has to be distributed over the core diameter of the fiber optic cable. So it has to be very precise light beam to be used for testing. In the old days, we used, for example, this kind of things here. This is the light scheme of a VCSEL laser, uncontrolled VCSEL laser. That's not good anymore for testing. We need this controlled light. It's LED light, which is filtered, let's say, a special way to have exactly this shape of energy dissipation. What is doing that stuff now, the job here? Just a picture of our multi-mode system we use with the Fibre Expert. You see what's very important here in the multi-mode is removable adapters here to match on the receiving side always the test connector of the fiber optic link you're going to test. What's also included for us is very important here, this cleaning stick here. We want to be sure that everybody gets kind of awareness. Make sure that all the connections are really properly cleaned before you do your first connection, okay? One question which is always raising again is, what kind of documentation do I need? Do I always have to have an automated report generation through high-level instrument? No, not necessarily. The standard also tells you what the documentation should look like and what components should be in your certificate. So you can use a manual instrument to do fiber optic measurements. You have to just to make sure that you use proper test cores, you use encircled flux modules, and you have to make sure that you're doing it properly and the instruments are calibrated. Then you can use it a manual document as well. You fill out, you sign it, and it's also a very valid test report for fiber optic measurements. Of course, the professional way is to use an instrument like the wire expert, as you see here. So these modules can be removed. Typically here are the copper modules. You just swap them against the fiber optic modules. What else the instrument is supporting, like we already saw on the qualifier, is the microscope here. Okay, there's also the software built into the wire expert to do the analysis of the 4 zones of the end phase. Very important for us. You can store it, you can put it to the measurement data. If you look to the screens of the wire expert, I just put it here on one slide. These are the 3 steps of how to get a proper measurement done. First of all, you need the configuration. The instrument helps you, it offers you pictures. What is the type of measurement you want to do, single-ended, both-ended? What's the field calibration you want to do, 1 jumper, 2 jumper, 3 jumper? There is a table you can fill out. How many connectors do I have? How many splices do I have? Here is to define what quality of category of fiber optic cable I use. So here is a tool. The instrument helps you to set up the instrument properly for the measurement you want to do. Then you do the set reference. Depending on what method you are using, you get different screens offered. And finally, you press the measurement button and you get very detailed measurement details out of the instrument for your fiber optic cable. And finally, where I want to end up with this one here, very nice reports here, which are defining what I have measured. And I'm going for this little green tick over there. Here you see the measurement results, bidirectional measurement results. And if we meet the requirements here, we also meet certain requirements for certain transmission standards as well. Here is how it looks like, the documentation for the end phases. This one here behind me is a summary page of measurements done in a row. Okay, that was attenuation measurement, the classical acceptance test for a fiber optic link. So what else can we do? We can do reflection measurement. Now we're talking about the famous instrument about an OTDR. So what you see here is reflection measurements from OTDRs. What is an OTDR? Optical time domain reflectometer. It's giving a characterization of fiber optic link as a function of length of the fiber. So you see a picture of your fiber optic, you see where are events, where is trouble. A few terms which used in this world is backscatter, refractive index, non-reflective events, reflective events, the fiber end, ghosts. Now we have ghosts, and we're using launch and tail cores. So these are the vocabulary used in OTDRs. How does an OTDR work, actually? OTDR is sending out pulses. There's a pulse generator built in that is triggering a LED, a laser diode, let's say, and sending out pulses through this directional coupler into the fiber optic cable under test. This is the fiber optic cable under test. And this fiber optic cable under test is answering with reflections. And with reflections coming back into the same port where we transmitted the signals, are just turned here into the detector here through this coupler, and the detector is amplifying the signals, is converting the signals, and here's a logic in the instrument that is combining the sent pulses with the timing of the received pulses. And what you finally get is this type of waveform of the link or the trace of the fiber optic cable. What you see here, what is important, the unit under test, the cable under test, is not directly connected to the OTDR. It's connected to a launch cord. And at the end of this unit under test, you see a tail cord. Why do we need this? We need this to give a clear indication of the last connector and to give a clear indication of the first connector. Because we have things like dead zones, pulse lengths, and so on. If you would directly connect the cable under test to here, you wouldn't see the first connector, because this will fall into the time when the pulse is leaving the OTDR. During the time the pulse is leaving the OTDR, the detector is not opened. Okay, and the reflections coming from here would not be registered in the detector. So to make sure that the first connector can be really detected, you need launch cords with certain lengths. Okay, so what can we measure with an OTDR? We can measure a lot of things. We can measure the distances and lengths to certain events. We can measure attenuation values. We can measure it automatically, or we can set cursors to do this. We can measure reflections of certain components, like connectors and so on. What is it used for? It's used for, of course, for installation and commissioning of fiber optic cables, and servicing and inspecting, and of course, fiber identification. You can use it. There are various fields where you can use an OTDR, of course. Okay, this is what an OTDR can measure, but an OTDR also can see things, and see means, in this case, again, you see it now for the third time, it can be combined with a microscope, and also the software for the microscope or the end-phase qualification and analysis is built into the instrument. It's a very important story to have a control about your end phases. Okay, and why is this microscope type so interesting? Because you can also measure behind the couplers in a panel. A lot of people only having manual microscopes where you just can see a connector you directly plug in of a patch cords, but they never have a chance to see the connector in the panel. So a lot of people never ever look into this one here, and this might be the troublemaker here. There might be some little dust on this connector here. So make sure that you can measure or analyze or see both ends, the panel connector and the connector which is connected later on. Okay, a few buzzwords on OTDRs. Buzzword like dynamic range. What is dynamic range? You see that the margin between the backscatter level at the beginning, where you insert your light pulses, and the beginning of the end of the fiber, the noise floor at the end of the fiber. Okay, so this dynamic range. The dynamic range is important for the length of a measurable cable. If you have a dynamic range which does not fit to the length of your cable you're going to test, you might not see the end of the cable or some events on the very last mile of the cable. So make sure that the dynamic range fits the dynamic range you expect in your measurement situation. Measurement situation means measurements. And there's also dynamic range and measurement range. What is a measurement range? It's a maximum attenuation of which a splice can be reliably detected with 0.5 of an attenuation. So to make sure that 0.5 of a dB, an event with 0.5 of a dB of attenuation can be measured properly, that's the measurement range. It comes down here, more down. You wouldn't see it here because it's disappearing in the noise floor of these trace you see here. So make sure that the measurement range also fits to your requirement and is sufficient enough also to see measurement attenuation effects at the end of the link. Two very popular parameters are event zones, dead zones. Event dead zone is the first one. What does event dead zone mean? This is the time the OTDR is blind to see the next event, the next reflective event. Okay, because when you come to a connector, so the pulse of the OTDR comes to a connector and gets reflected, it's filling up the detector at the instrument, and the detector is full. And this is why it's showing this high amplitude here. And it takes a certain while until the detector is empty again, or is going more empty again, until the next reflection can be stored in the detector and can be analyzed. So if there are two events very close on the fiber optic link, and the first event is causing a lot of reflection like a connector, the detector would be full and would not see the second event properly, okay? And so there is a definition, it's called event dead zone, after what distance you can see again a reflective event. So for example, a good event dead zone for an OTDR used in the LAN environment is below 1 meter. So you see connectors which are sitting about 1 meter in distance. For example, you can see patch cords in between of your fiber optic link, for example. Okay, if the dead zone is too long, you wouldn't see these connectors in between. So you would only see one funny pulse and that's it. The second important dead zone is the attenuation dead zone. So when can you clearly detect a attenuation caused by a splice, for example, clearly after a reflective event, after a connector? So a typical good attenuation dead zone for a LAN instrument is in the area of around 4 meters. 4 meters helps you to detect the splice quality of a link that has a pigtail with about 6 meters, for example. So there's certain reasons for certain lengths. So remember, event dead zone below a meter, attenuation dead zone around 4 meters. Okay, resolution. How short can your pulses be, and how many pulses can we put in one row? This has to do with the length of the pulses. If the pulses get too long, too much energy, you might miss events which are very close together. Okay, so you have to make sure when you're testing on a LAN environment also to use pulses short enough to allow for the detection of two events which are very close together. So when you're testing a 100-meter link, it makes sense to go down to very small nanosecond pulses. The lowest pulse width the instrument is offering go to 3 nanoseconds, 4 nanoseconds, whatever the instrument has. If you go to 100 nanoseconds, you wouldn't see the events when they're close together. You would see, just as you see on the lower two lines, one reflection coming back, and you don't see the two events. So the pulse width is a very important feature. Okay, launch cord, tail cords, I mentioned already, they're used to allow that the pulse leaving the instrument is stored, let's say, on a cable before it hits the first connector, or to make the last connector visible with a launch cord at the end of this. These launch and tail cords are standardized. You see there are two lengths in the standards, 150 meters for single mode and 75 meters. Actually, we are using a bit longer cables nowadays to make sure that the whole pulse can really fit into the launch cord or the tail cord and gives you a clear indication of the first and the last connectors. Very important. So always use tail and launch cord to get a clear view on one shot of the cable system. So what is now the instrument look like doing all these very nice measurements? Here you get a picture from the OTDR 5000 Fibre Expert, as we call it. It's a quad instrument, so it works for multi-mode and single mode. It has the typical wavelengths to be used there, 850, 1300 nanometers, 1310 and 1550 nanometers. Okay, there is a specification sheet of the instrument. I don't read all the lines. Let's just go for the major stuff here. Let's have a look to the event dead zones and the attenuation dead zones. So the event dead zones are below the 1 meter. That's good, fantastic. The attenuation dead zone is about 4 meters. That's good to see even pigtailed cables. That works very nice. Okay, the dynamic range of the instrument is 26, 24 dBs. That's fantastic. We never have a loss budget in a LAN environment that's going up to 24 dBs. That's not happening, definitely. Okay, so the rest is typically specifications for the instrument. I don't read it now. That's one way to present the measurement, is this style of traces we have. So we always saw traces now. Nowadays, there are a lot of people who don't want to handle traces. They want to have a different kind of display. Therefore, the instrument offers the so-called Smart Link Mapper SLM functionality, which simplifies the readings. So you don't see now these actual trace. You see for all events on your line, you see these little icons. So you switch from trace view to an icon-based view. Okay. The older generation, like my ones, we are enjoying the traces because for us, this is a picture of the real life. A lot of people nowadays are more happy to see the icons, just to see the icons and see the table underneath to see the events. Okay, whatever, the instrument provides both ways to do this. What do we want to get out of the instrument? This one here. This is the certifications out of an OTDR. Very important. You see the picture of the trace of the fiber optic link, and you get the table here with all the events detected automatically by the OTDR. That's proper documentation you get. Here are a quick marketing slide. So what do we get with the instrument? If you buy an instrument, the instrument, some shoulder bags, carrying case, and so on. What you need what you should have, what we always highly recommend is get yourself a microscope. It's very important to get the microscope data. Launch and tail codes, we have different versions on our offer. We have even one with steel armoring around the cable, so for rough environments to be used. And what's also important is different adapters here on top of the fiber optic modules. You can swap these adapters if you have a different interface. So, okay, that's it basically from the technical discussion today. Here again, a little view to our little series of small seminars, autumn seminars. We're almost through the whole list. Here are we today. Tomorrow we are going to talk about active Ethernet networks, so the basics of active testing as we provide in our instruments. As I said in the first week is to get a network up and running, to talk to switches and to include into systems. Okay, so that's from my side. Thank you very much for your attenuation. We are a bit in overtime. So this is why I'm asking now my co-pilot Matthias to come to the stage again, and let's do the question.
Yeah, thank you very much, Alfred. Was very interesting for me as well. You already answered some questions during your presentation. One was one jumper, two jumper, three jumper. Will the device guide me through this process? You showed it on one slide that all the devices which are doing tier 1 measurement, so which is the real attenuation measurement, they will guide you through this set reference process, one jumper, two jumper, three jumper. That's fine. The other thing I have to answer, because it comes via the questionnaires, is yes, the microscope, it's only simple plug and play for the wire expert, but take care, not the wire expert 500, because it's only copper based. You have to use the wire expert 500 plus. You need a fiber license to use the microscope, and you need an adapter, a special adapter for that. It's available in the price list. Then you can use, or you have the single mode or multi-mode measurement adapters in it, then it works fine. But you need a microscope adapter in the device of the wire expert to tell him, yes, you want to measure fiber, and otherwise it will not happen. On the other hand, the microscope will work with the OTDR you just mentioned. It will also work with the new Link Expert series, and it will also work with the Net Expert series, so with our qualifiers. So you can use the microscope in every device. On the other hand, one question is, I know the ISO 11801 standard. What is the difference to IEC 14763-1, and what is the right standard for certification?
Yes, both standards are right, because they're talking about different things. The ISO 11801 always gives the limit values, and there are always measurement standards who will tell you how to do the measurement and how to test against these limits. So, and in fiber optics, there's a little combination between the limits plus the limits in the ISO 11801. So there's a little bit of mixture of this, but actually the ISO always gives the overall limits of the transmission of the cabling, okay? And the ISO standard, the 14763-3, telling you how to do this, how to get to these values. So the ISO doesn't tell you you have to use one jumper, two jumper, or three jumper. That's defined in the measurement standard in the ISO 14763-3. Okay, this is the way, the cookbook, how to do the measurement properly.
Okay, yeah, fine, thank you. And yes, I want to address to you, if you have any further question, if you have any questions to standards which starts with 1.4 or 1 or 11 or whatever, give us a call, call Alfred, call our technical department, our support people, call me as well. I will hand you over to Alfred then later on, so that's okay. But give us a call, ask the questions. That's from my side, so thank you, Alfred.
Yes, you're very welcome. Thank you very much for the questions. And as mentioned earlier, maybe see you tomorrow again to the last session of these things. Oh, you lost your glasses. Yeah. Okay, so from my side, thank you very much again, and goodbye. And I'm moving away from the stage.